time to start. And it's my great pleasure to introduce our today's speaker, Tomasz Maciążek. Tomek is my PhD student. He started to work in CFT around 4 years ago when he was still a student at the Warsaw University. He did a master thesis with me, and now he's actually finishing his PhD. And the subject of his today's talk is partially connected to this PhD. Actually, he will explain some ideas behind this PhD thesis, so that they are more maybe I don't know. So these ideas will be described in more physical sense, not mathematical, not to bore you with a lot of mathematics once again. Okay, so
okay. So
sorry. There is one more announcement. So we have a microphone here, and so it's actually quite important that when you want to ask a question, you have to raise your hand and take this microphone, because otherwise nothing is recorded. Your question is not recorded, and it's really a poor quality of those videos which we put on YouTube. So basically, you raise a hand, you get a microphone, and then you can tell whatever you want.
Zgodę na to, jak się ma zarejestrowane, to każdy musi wpisywać kartkę. A jak teraz wszystko będzie nagrywane, to czy wszyscy napisali?
Okay, so thank you for this introduction. So this talk will be about how the topology of configuration spaces leads to different kinds of quantum statistics. So the quantum statistic is the physical part, and the topology is the mathematical part here. So the general problem, or the general setting that we have, is some wave function defined on a topologically non-trivial space, and this is the source of all the quantum phenomena that we explore. And so we have some space, some domain of the wave function, which is topologically non-trivial. So, for example, it is a sphere, or a plane without a point, or a plane without a disk, or a two-dimensional torus. And we define a wave function on such a space. So, and points from this space are arguments of the wave function, and the space is, in general, describes the spatial degrees of freedom of some system. It's just absolutely abstract what system it is, and the setting will mostly regard like a single particle, but it's an effective particle. So, but I will explain it later. So for the most part of the talk, we will consider scalar wave functions, that is, wave functions which are valued in complex numbers. And there will be no classical forces in the physical system that we consider. And this thing means that there is a connection one form on this space M whose curvature vanishes. So this means that these particles are not subject to any classical force. And in the general form of Hamiltonians that we consider then, when we have this space M and some flat connection, then the Hamiltonians are, the general form is like 1 over 2m when m is the mass of this effective particle. Momentum, which can have many components, because it depends on the dimension of the space.
Concern this no classical forces. The magnetic field is not there.
So magnetic field is there, but only if the connection form is flat. So it's
B is 0, but A can exist.
So yes, so when we are in a region where there is no magnetic field, but
since B is a physical force, not A. Yeah, then the magnetic field is not there.
Yes, it's not.
So the answer that there is A is meaningless.
Yeah. Okay. So, but it might happen that there is magnetic field somewhere, but not in the region where this wave function is defined. So. Okay, so this is the Hamiltonian. So what happens when we look, for example, at one particle in Rn, defined on Rn? Then it's perhaps it was Dirac who first noticed that if we shift the momenta by the coefficients of some closed one form, such a transformation, so pi is changed to pi plus gamma I, where gamma I are coefficients of some closed one form. Then such a transformation does not affect the commutation relations. Okay. So, but this transformation is not relevant when the domain of the wave function has a trivial topology. So in this case, when this is Rn, Rn is contractible. So it doesn't matter. And in order to see this, suppose that we have a we have some Hamiltonian, and we have a wave function who is a solution to this Hamiltonian, but with momenta which are not shifted. So this would be this psi of x. This would be an eigenfunction of some Hamiltonian h of xp. And if we transform the momenta so that we add this connection, so that we add the coefficients of this one form, then we can remove this transfer. We can take this transformation back by gauging the wave function properly. So, and this gauging is the following. We know that when M has a trivial topology, then this one form can be written as the derivative of some function, and we put this function in the exponent in front of the wave function. And then in this transformed Hamiltonian, we have momentum operators, which are p tilde, the shifted ones, and we add on the gauged scalar, this gauged wave function, and what we obtain. So this is precisely what we have. This is the expression, and so if the derivative hits this expression here, then first we get the derivative of f of x times this wave function. Okay, then the derivative hits the wave function here, and then we have plus gamma I times this expression, and these terms cancel out, and so we get that it's just this phase factor which goes in front of the pi times psi of x. So if this is the eigenfunction of h of xp, then this expression is the eigenfunction of h of xp plus gamma of x. And so we get some global, just some global phase in front of the wave function. So this is for trivial topology. This is irrelevant. However, if the topology is non-trivial, so for example, consider one particle in R2 minus some disk taken out. Then, in order to see this non-triviality, okay, so first recall that the transport of a wave function is generated by momentum. Okay, so if we take e to ip delta x and we act on it on psi of x, then we get a shifted wave function. So but if you want to do it in more general way, so what we have to do, we take a wave function and we take a parallel transport of this wave function along some curve, and then if we solve the equation for the parallel transport, then we see that it results with the multiplication of the wave function. It's shifting plus multiplication by such a phase factor, which is the integral, over this connection one form here. So, and this is relevant when we consider transport along loops. So, for example, when we have a transport along some contractible loop, then what we get here is the integral of a one form which is closed along a closed loop which is contractible. So by Stokes' theorem we get that this phase factor is 0 because we integrate this one form along this contour, and by the Stokes' theorem it's the same as integrating the derivative, the d gamma in the inside of this contour. And, okay, because d gamma is 0, then this integral is 0. Then this means that this integral is also 0. Okay, but when we take a non-contractible loop, which means that this region inside the loop has some hole, then by the Stokes' theorem we have the integral over gamma is equal to the integral. Sorry, this integral. Okay, so we have the integral over S gamma, d gamma is 0 because gamma is closed, but this, on the other hand, from Stokes' theorem, we know that this is the integral over the boundary of S gamma, of gamma, and the boundary of S gamma in this case is the boundary of this hole here and gamma. Okay, so what we get then is the integral over gamma of gamma minus the integral of the boundary of S. So, okay, so and this is clearly non-zero. So we get that this phase factor by transporting the wave function around the loop is non-zero then. Okay, and so what we did, we transported the wave function around the non-trivial loop, and we got some phase factor in front of the wave function, which does not depend on the loop actually. Okay, so because it depends only on the integral of this, of the boundary of this S. Okay, one can ask whether there exists like any physical scenario where this is applied, and this is, for example, a Aharonov-Bohm effect. And the setting here is that we first consider a box which has some Hamiltonian, and suppose the boundary conditions are that the wave function vanishes outside the box. The solution to this Hamiltonian is, so we get some set of eigenfunctions, okay, which are defined only in this box. And now imagine that we put this box, then we have a similar situation, but the box now is put in a larger context. So it is put on a plane, so it's a two-dimensional box, it's put on a plane where somewhere outside of this box there is a hole where a magnetic field appears. Okay, so where there is some magnetic field. So in the region where the box is, there is no magnetic field, but there is some non-vanishing. If you solve the magnetic vector potential, if you want to find it, then it's non-vanishing outside of this hole. Okay, so and this is precisely the connection one form that we have. And when we transport the wave function along such a loop slowly, when we transport the box, which is in some state psi n, then we get some phase factor. And how this thing happens? So we know the solutions for the box without the field, and the solution for the box with the field come from this gauge, come from multiplying these wave functions by this integral, which is so this is precisely our f of x that we had before. And now, so to get this f of x means that if you want to know the value of this wave function in vector r, at point r inside the box, it means that we have to integrate this vector potential from capital R to this point r, okay? And so we get the function f of x. And we multiply the previous wave functions, which are now functions of the difference of those two vectors. So now our wave function depends parametrically on this large R. And now what we do, we transport this box around the loop, some non-trivial loop, and we get some Berry phase. This is the formula for the Berry phase. So if we compute this integral, we get that this is precisely Q over H times the magnetic flux inside this hole here. So this is the physical context. Okay, so we had this transport of the wave function, which resulted with some phase factor, and this phase factor is the Berry phase that is obtained in this physical scenario. So this is just some example, one particle example. And the idea to explore these phenomena further is to consider object which is called a configuration space of identical particles. And this has non-trivial topology. So this space is constructed in the following way. So normally, classically, when you have a number of particles, and each of the particles which are placed in some space M1, then in the standard approach we get, so what we take as a configuration space of those particles is just the Cartesian product of the one particle spaces. But first of all, to make the particle indistinguishable, identical, we divide this Cartesian product by the action of the permutation group, which means that we identify, so we have like some configuration of n particles, which is 8x1 xn, xi is in m1, and so this is such a tuple of coordinates is in a relation with say x1. So if there was xi, xj here, then this tuple is in relation with xj, xi, and so on. So if we permute the particles, then we get the same point in the configuration space. But in order to do this properly, we have to subtract something which is called diagonal, which means all points that are points where the particles collide. Okay, so we do not allow the particles to collide. So again we take the Cartesian product, subtract the space where particles collide, so where any of those coordinates overlap, and we take the quotient over the permutation group. So this is So this is the fully abstract definition. I will go to the examples soon. But so what we explore is that this subtraction of the diagonal, not allowing the classical particles to collide, when we consider a wave function on such a space, then we have those topological phenomena, because this space has
collide, but occupy the same point.
So,
that's different.
But if these functions are continuous, then this condition does not seem to be relevant.
The wave functions?
If these functions are regular, then the fact that at equal points something happens does not seem to have mathematical meaning.
So you mean when the wave functions are... regular? Or sorry.
The remark is,
Yes.
suppose we have a function for two particles.
Yes.
Okay. Now, if this is properly continuous, then its value at x1 equal x2 is not very relevant.
Yeah, but the value is maybe not relevant. So we can always, when we have a wave function which is just defined here, and then it is also, it has some regularity properties, then it's also well defined here.
Yeah.
But the main point is that when we transport such a wave function around some hole in this space, then we get some effects which are not present when we just take some contractible space. It's like, so like in this example of the Aharonov-Bohm effect. So if we just take R2, there is no phase, okay? And when we take the hole out, when we just cut out some hole inside and we take the loop, then there is some phase.
One small comment. So the removal of this set delta, so of all those points where particles are at the same place at the same time and so on, it affects the topology of this space. And by affecting the topology of this space, we can observe some non-trivial quantum mechanical properties.
But what is the physical meaning of the condition that we remove the space of when all particles, I'm sorry, I'm still thinking about the two particles. When two particles are sitting at the same point, what is the two particles by a construction of a physical particles cannot sit at the same point?
Exactly, that's why we remove it, because we treat them as a
yeah, but that
particles.
cannot.
And this is a classical configuration space, so at classical level we can say it.
So all configuration spaces are in a sense classical.
Yes.
Because the positions commute. So the word.
So it's just.
Like in a classical.
So what I would like to say is that so in general in physics we do not consider this set, okay? So
but that's not the same situation as the plane where I put a solenoid with the magnetic field inside, as in the case of Bohm-Aharonov.
No. So it's not.
You see the words, but the fact the Bohm-Aharonov effect is something which we can do in the laboratory.
Yes.
Without cutting any holes by using a solenoid.
Yes, but
then the conditions, this topological condition, has a very precise physical meaning, and it's very different from that.
Now we have to agree on something different.
Yeah, then I got to, no, but there was a reason why the Bohm-Aharonov-Bohm.
So there is exactly a very good reason why people remove this diagonal, because now he will tell what are the implications of this procedure.
yeah, so it's
For many particles.
Okay, so
And then
there is some assumption that let's see what happens.
yeah.
That's the point.
So okay, I would just like to add that okay, so maybe just this removing the diagonal is always there, but people just didn't consider it. So I mean, it was always implicitly in those physical phenomena. So if we just do it right now and consider configuration space, wave functions on such a space instead of Cartesian product, then we will like get those phenomena in a more consistent way.
But since you are using these two different versions, the question is, where does physics come in? When we have a wave function, how can we tell whether we should remove this or not? We have two bosons. And
Yes.
which picture is correct?
Okay, so what this...
There must be some way of judging whether one way of approaching this physical problem is correct or not.
Yes. Okay. So what this says, it says that okay. So we have this definition, and we will have some implications of it, and it means that there.
The question is, I mean,
there might.
in the case of a
The question is whether this definition is motivated by something.
Yes. So it is. Yes. Yes. It is.
Yeah, but how do we manufacture it? In the case of the Bohm-Aharonov, then in spite of this, we can manufacture. We know exactly what is the physics behind
Yes. Yes.
gammas,
closed forms and everything.
Okay. Yes. So
Usually in physics one starts from physical problem.
yes. So there was.
Okay, so when
okay.
show the next slide, and then we will see what we want to say.
Okay. Sorry. Okay. I just.
Don't elaborate about this any longer. Change the slide.
Okay. But.
Please.
But yeah. Just one remark that this space is nice because loops in this space correspond to exchanges of particles. So this is what will give rise to what we call quantum statistics.
Those particles are identical?
Yes, they are identical. So this is what.
Identical, indistinguishable.
Yes.
Yeah, normal. Maybe Fermi.
Maybe Fermi.
It is what happens actually. It is assumption
That in physics there is something what's called speedless Fermi.
Okay, sorry. So maybe let's proceed to some examples, and so we will have fractional quantum Hall effect, which will be the physical motivation. But here, so let's just maybe to gain some intuition, look at two particles in R2. So we have two particles on a plane, and we want to see what this configuration space of two particles is. So we have two coordinates, x1 and x2, that point to those particles. So this is not nice, but we can find some nice coordinates where the space can be expressed in a simpler way. So what we do is we take the center of mass, x1 plus x2 over 2, and the relative position, x2 minus x1. Okay, and this is what we capital R is the center of mass, and small r is x2 minus x1, the relative position, and then so note that this is this should be 2. That this quantity, the center of mass, is invariant under permutations of the two particles. So this coordinate factors out in this space, and what we are left with is the relative position minus 0, because we do not allow the particles to collide, and
what does it mean there to collide? They sit in the same point.
Yeah.
Physically very different. That I already said.
Okay, so yeah.
They sit in the same point.
Yes, sorry. So we do not.
I believe this is the.
They occupy the same point.
Yes.
They do not. I believe it's a certain physical problem which was there. I believe it was pointed out in the 30s when the problem of quantum statistics came into existence.
Yeah.
And I believe it was a Stickelberg who made that comment.
Okay.
That if I permit the particles to sit at the same point, then and if they are indistinguishable and so forth, then the question of a statistics become meaningless, because there is no physical way to tell which particle I exchange with which. And that is probably the reason why you are removing this diagonal. Because I mean, if you allow, which is completely unphysical, because the particles have a finite radius, and the quantum mechanics precludes them from sitting at the same point. But if they are point physical imaginations, and if they sit in the same point, then the notion of exchange of the particles is completely meaningless. And probably that is, I don't know, I mean, but that would be my argument why I would try to remove this and see what happens further. Because, I mean, there's no way to tell it. What I exchange with what?
One of the, maybe not a paper from 30s, but from 70s, when this topological approach to quantum statistics was first described, paper of Leibniz and Mirren, they actually say that
it was described much earlier by David Mermin, and the whole business with anyons and everything was known much earlier than mathematicians touched.
But they are not mathematicians, they are
never mind. But the concept of a statistics related to topology that existed in the solid state physics years before this this thing has come into existence.
Okay, so yeah, so let's so we do not allow the particles to sit at one occupied.
I don't understand this phrase. I have a wave function, and wave function is a well-defined continuous function of the argument.
Yeah.
How can I tell whether this wave function allows for the particles to sit at the same point or not?
So no, I cannot tell it from the wave function. I can just
This
maybe.
is the reality. We have the wave function that describes the state.
So when we,
Now we are saying something that we do not allow the particles to sit at the same point.
So,
But can I tell this
We're not discussing.
looking at the wave function?
Not yet.
This is just a topology of configuration space.
okay.
The wave function is defined on this configuration.
They are thinking different.
And I have a given function.
I think I stick to my problem. I have a configuration space for n particles, and these are
two.
Okay, let's talk about it. And these are not real particles. These are mathematical imagination, which allows those particles, I don't know how, but there is assumption made, that you can put those two particles at the same point. Now, if they...
What does it mean, quantum mechanically? Quantum mechanics?
It's mathematical game. We have... So let's not use the word particles. Let's use the word points. I have points in the space, right? Which I labeled with the red color, x1, and blue with the x2, right? And if I put them in the same place, then
Colors merge.
the colors merge and I have no way of telling.
And it becomes green.
What?
It becomes green.
Okay, so let's talk about the three parts.
Okay, so I don't know. So so classically it's more or less intuitive what it means, but quantum mechanically we just say that we do some quantization of this problem, and we just, in the sense that we just consider wave functions on a different space, and just see at the implications of this fact. Okay, so returning to this problem of two particles in the plane, so we have this center of mass times the relative position minus 0, and we take the quotient by the permutation group. Okay, so it's a little riddle what this might be when we identify opposite vectors in R2. So this becomes a cone without apex, and the topology of this space is non-trivial. So it's the same as the topology of a disk, or okay. So some non-trivial loops correspond, for example, by fixing the center of mass of two particles. So we have two particles, and we keep them in the same distance, but we exchange them like this. So here on this picture, it would be a loop which is at which corresponds just to rotation of this relative position.
But this space is the configuration space for one single particle called the photon.
Yes.
And this is precisely what Barry phase is like for the photon.
Okay.
You don't have really two particles, but just one, it's enough to have the cone. So I'm not criticizing, I'm just saying that what you are saying has a very nice interpretation in terms of a single photon, which does have this topological phase. And it has been measured experimentally by Chow and others.
Okay, so yeah. So this is like one problem of this approach, that we have to find the physical scenarios.
The connection for this was given in our book in '76, Quantum Electrodynamics. There is a nice connection, and the curvature of this connection is non-zero.
Okay, it's non-zero. Okay. Oh.
So if the connection is not zero, then
the curvature is not zero.
curvature is not zero, then we are coming back to the first slide. which said that this is not the same case because he insists that the curvature is flat. So
But then it's not the light group.
So this is for the photon it's not a topological phase, it's geometrical phase.
Yes.
So because this phase depends on the loop which you choose.
Yes, and this is why when you...
And here he is speaking about the phenomena when it only depends on the homotopy type of the loop.
Yes.
So if two loops are in the same homotopy class, they get the same phase.
Yes. Okay, so this is
So there is this
reason why they have to distinguish between topological phases and geometrical phases.
Sorry, I think I should have opened it in a different program. Okay, so this should be gray, the whole area. So maybe just a little detour from this for these mathematical considerations. So an example of precisely of this scenario where two particles exchange and they gain some phase is two anyons in fractional, for example, in a fractional quantum Hall effect. So the Hamiltonian of this system is the Hamiltonian of a number of electrons and electrons on a plane where there is a perpendicular magnetic field to this plane. And they interact via Coulomb interactions. So this is the Hamiltonian, and Laughlin proposed a wave function which is an approximate solution to this problem. And this wave function has, so Z1 to Zn are the two-dimensional coordinates of n particles, of those n electrons. We just put them into a complex form. And the wave function has this form, it's unnormalized. So this would be a family of ground states that are numbered by odd numbers m. And the excitations are obtained, for example, by multiplying, picking two coordinates, picking some coordinate on this plane. So W1 is some fixed coordinate on the plane, and we create this expression W1 minus Zi, the product of those expressions, and this means that there is an anion with coordinate W1. So physically, to see this anion, so it means that when we look at the electronic density, this results with a zero of the electronic density. So it's it means so this somehow.
But it would be prudent to tell the audience, which might not be familiar with the notions of the fractional or even not fractional quantum Hall effects and the word of anyones, to tell that this Hamiltonian was just for the electrons.
Yes, it was.
It was written for two anyons. No, this is the Hamiltonian for electrons.
It's not a Hamiltonian.
There are no anyons in the nature.
No.
They don't exist. Well, it's written two anyons. No, this is the Hamiltonian for electrons.
No, so we will obtain
for many electrons on a plane with a simple magnetic field.
Yes, this is true.
Since everything is recorded, there is a recording of the seminar for the PhD students, which we had here systematically, on which exactly the derivation of that kind of a structure was discussed by our younger colleagues. And it is nothing new. It's written in the book by Gombash from the 50s.
Yeah, but this is just an example he was
but why to use the words which are, for most of the audience, very empty?
But you just said that everyone attended this seminar.
No, PhD students, and I don't see them here.
No, so
so that makes a difference. I'm very careful of what I'm saying.
No, but
the simple using words that this is a Hamiltonian for anyone's and for the fraction. Where is the notion of a fractional quantum Hall effects needed for this presentation? Nowhere. I mean, the fractional quantum Hall effect has a completely different meaning. It has nothing to do with this Hamiltonian. There's one of the possible effects which can be described. But that is like saying that the Schrödinger equation describes a fractional quantum Hall effect. This is pretty
It is,
which is true. I mean, what you write to students who write the Schrödinger equation?
No, you didn't wait until he will tell what he actually wants to do with two anion excited wave function, because he wants to calculate a phase which is gained when those anions are exchanged with each other, and to show that this is actually a topological phase.
These are not anions, these are N1s. Anions are something completely different in physics.
It's the matter of pronunciation.
Yeah, but we... Okay. Anyway.
Okay, so maybe Tomasz continue.
okay, so so if someone is not familiar, so it's just imagine we look at n electrons with this magnetic field and interacting via Coulomb interaction. So this, and we have an approximate solution to this Hamiltonian, and the excitations are created by considering such wave functions, just multiplication by such terms. And if we take just one such term, it means that we have one anion, an excitation which is type of one anion. When we have two anions, then it means that we take two numbers and we multiply those two expressions in front of this old wave function, and this is what we call two anion excitations.
What is the meaning of small m?
Small m is just integral number. It just parameterizes those ground state wave functions. It can be an odd number, any odd number. Okay. So the anions in this model are collective excitations of electrons. Okay, so and this is a good setting to.
Actually, this function is. What is that? This function, the Laflin function, is very easy to understand. You solve a Schrödinger equation for a single particle in external constant homogeneous magnetic field. You get one certain function. Okay? You write it as a function of it because it's on the plane perpendicular to the field, because it's a plane wave along the field. Then you can write it as a function of a complex number z. Okay? And then you take n of them, and you calculate the Slater determinant, which is the wave function of the n particles in the simple non-interacting case. Bingo, that comes to the Laflin function. And for that, Mr. Laflin got the Nobel Prize.
Yeah, okay.
Calculating the Slater determinant in the proper coordinates.
Yeah, okay, so so we have this wave function, which means that what we call this, it's two anions, one localized in W1 and the other one is parameterized by W2. So let's imagine that so they are just one and two, first anion and the second anion, and so this C2 of R2 would be the parameter space of those anions, those W1 and W2. And what we do is we want to exchange the parameters, exchange the anions, so we can either fix one and take a loop around the first one. So it's easier for the computation, but it's actually the same thing as exchanging them in this way, that the first one goes here and the other one goes here. It's like two times those loops, it's this loop. And we can, because there are parameters, we fix W1, W2 depends on time, and we compute the Berry phase. And what turns out, so we can compute the Berry phase first when the loop encircles the first particle, and the second Berry phase when the other loop doesn't encircle the first particle. So if 2 does not encircle 1, the Berry phase is minus 2 pi times the number of electrons inside this loop. And otherwise, if we have this situation, then the Berry phase is this expression plus 1 over m. If we subtract those two situations, then we get a loop-independent expression, and it's always pi over m. Okay, so this is the phase that is gained by exchanging those two anyons. So this is and 2 pi, but the loop is 2 times a single exchange. So this is okay.
So this is just a simple calculation for a given wave function.
Yes, yes.
Yes.
So it's okay. So we kind of before that we knew that there are those non-trivial wave function, non-trivial loops, and we want to find some physical phenomena where this phase that comes out when we transport a wave functions around the loop is actually physically relevant, and this is an example of such a.
And the important point here also is that this exchange phase does not depend on this loop.
Yes.
So for loops which can be, so this is a topological phase. So that's why he's presenting it. This is an example of a topological phase.
Okay.
And at least in the case of the Laflin wave function, one can see what does it mean to exclude the points that coincide, because then zero, the wave function is zero.
Okay. So the general setting that we explore is the notion of the fundamental group. So it's a group of loops in a space with the property of composing the loops. Okay, so when you compose the loops, it's a group. It's a group action. Okay. So for this cone that we had for the two particles in R2, we get that the first fundamental group is Z. So it means that there is an infinity of representations. But when you take two particles in R3, then again we have the center of mass, but then we identify opposite vectors in R3, which is the real projective plane. And this is the first fundamental group of such a space is Z2, which means that there are only two representations of the first fundamental group. So this means that, then one representation corresponds to fermions and one to bosons. So one of them, when we exchange the particles, gives phase e to I pi, and the other one gives phase e to 2 pi, e to I to pi. Okay, but in general the problem is more complicated. N particles in R2, so this is something which is called the braid group. It's a group on n-1 generators plus a number of relations between the generators. And n particles in R3 is just the permutation group. But what we are actually considering in those examples were abelian quantum statistics where we assigned phases to loops. And the phases were assigned in a consistent way with the composition of loops. So where we have two loops, then the phases add. So mathematically, what we are considering were abelian representations of the first fundamental group. So this is what this expression means, and those abelian representations are the same as the first homology group of this configuration space over integer coefficients. And in general, if we want to classify such abelian representations, what kinds of phases can we assign to loops? We get a number of representations where we can assign any phase, and a number of representations where the phases are at modulo some number. So if we had Z2, then it's modulo 2. It can be modulo 3, 6, whatever. So again, for the plane we had just a number of representations when you can assign any phase. Those were those anyons. For the abelian representations for particles in R3 are Z2, and one is bosons, one fermions. An interesting example is the sphere, n particles in a sphere. This is Z to n-2, and those representations are generated by 2 minus 2 roots of unity, and there are always bosons which correspond to 1. There are always fermions that correspond to omega to the power n minus 1. And there is a number of other fractional statistics, abelian statistics, that depend on n. So this suggests they might be unphysical, because we wouldn't like the statistics to depend on the number of particles, I guess. Okay, and another conclusion that we can draw from this setting is the classification of different kinds of particles on topologically non-trivial spaces. So what we call a class of particles is actually a class of complex vector bundles, isomorphic vector bundles. So we view a wave function as a section of some vector bundle over this topologically non-trivial space, because it means assigning a point to each, assigning a number, a complex number, to each point of this space. So we can view it as a section of a complex vector bundle. And if we classify non-isomorphic vector bundles, they correspond to classes of wave functions that cannot be transformed into each other in a continuous way. So this is what we would like to call topologically different kinds of wave functions or of particles. And there is one nice theorem that classifies one-dimensional complex vector bundles completely, and this is just by looking at the first homology group. This is what we already had before. And what we are interested in are the vector bundles that allow flat connections, because this is they would allow to construct theories without classical forces, and these correspond to the torsion of the first homology group. So this is something different in the story of anions. Just looking at the torsion, so this is a bit different. One example of it is I had this example, but I don't have time to tell you about it. Okay, so suppose we
actually have time up to 5 past, because we started 5 past, not at 10.
Okay, then. So.
And a lot of interruptions.
Okay, so how to get bosons and fermions in the two particles in R3 are only bosons and fermions. So we had that this space is the center of mass times RP2, which is sphere, where two opposite points are identified. And what are the one-dimensional complex vector bundles actually on this space? This is the relevant part. Okay, so this is R is with relation of minus R, when R is in S2. And the complex vector bundles, one-dimensional ones, are of this form. To each point of the sphere, we assign some number Z, complex number Z, and this can be in relation with minus R and plus minus Z. And this is what we would call eta plus or minus. Eta plus are bosons, and eta minus are fermions. And how can we can tell this by looking at the sections of this line of this complex vector bundle. So if you take a section, psi is the section, and then this psi on the sphere, psi of R. So this is what. Okay, so this relation would mean that R psi of R is in relation with minus R plus minus psi of R for any section of this bundle. And this R was the relative position, which means that when we exchange the particles, then the wave function gains either plus or minus. So this is, if we pretend that we do not know that there are bosons and fermions only, then this is how we could get it, and using those arguments. Okay. And if we have those, so our program would be to find the non-isomorphic classes of vector bundles, and then see what kind of statistics they have. And to do this, we look at the holonomy group, which is the following group. We have a wave function, which is in general now, it can be d-dimensional, a d-dimensional complex vector bundle. And we transport this wave, we take a parallel transport of this wave function when there's flat connection along a loop, and we get some different vector than the starting one. And this vector is transformed by some unitary matrix, and those matrices constitute a d-dimensional unitary representations of pi1. So for d equal to 1, if we have one-dimensional representations, then we have abelian statistics. If the wave function has more components, then we have some non-abelian statistics. And for example, when we look, okay, so but there's a significant difficulty in this approach, because finding those non-trivial d-dimensional complex flat vector bundles is difficult. But in general, we do not know if they exist, but what tells us that they might exist is the torsion in the higher cohomology groups. And actually, there is an example of such a space that has torsion in higher cohomology groups, and this is the plane. And if we take n particles on a plane, so for example, look here. If we look, so we need 6. Actually, we have to look at the even cohomology groups. If we take 6 particles and if we take 6 homology group and 10 particles, this is okay. This was computed in 1970 by Arnold, and it was inconclusive. It was 6 or 3, Z6 or Z3, but certainly there is some exotic torsion here, and if this corresponds to some non-trivial flat vector bundles, higher dimensional ones, that this might indicate that there are some new types on particles that obey some non-abelian statistics on the plane. But okay, okay.
They are very well known.
Okay.
I mean, you are standing on.
Yeah.
I'm exciting them now.
You mean like
the torsion is related to the fact that in a lattice, which has a topological defects like dislocations, there is torsion. And it's not a abelian statistic, and if you want, there are books thick like this, describing all these properties in there. And nobody uses the words colored rates. At least I know, but now there are people who are using. But I mean, it gives nothing new to physics of this problem, right? The torsion, yeah, but the physical system, which has the non-abelian.
Yeah, but
the torsion in this context, the word torsion is not connected to some torsion tensor or whatever. That just means that some group is it's a finite part of a group. So
yes,
the group consists of a component.
If the torsion was used not in the sense of a torsion, then I'm terribly sorry, but
in mathematics it's used in a
but I mean, since torsion is also used in other parts of the mathematics, then that would be nice if, using the word of torsion, someone mentioned which meaning of torsion is being used.
Okay.
Because I mean, we can. Otherwise, we are losing our way of a communication if we are calling different things differently, right?
Without what?
okay, yeah. So
no, without the proper dictionary, the torsion
yeah, so maybe I
now
thought
should mean something different. And particularly that in relation to this. Show your last slide.
Okay, so I should have said it. Yeah. So okay, so So now I wanted to like shortly pass to this to what we do in our group. So we want to, because there's this difficulty in finding those vector bundles. We want to use some discrete models to see what happens, and the easiest thing to do it is to consider particles on graphs. The configuration spaces have discrete versions of them, and then the computation of homology groups is just operations on finite matrices. I mean but it's still difficult, but it's more doable. So the first homology group was computed by Adam and his colleagues some time ago, and also using different methods by another group. And what we do now, we want to look at those higher dimensional vector bundles. Okay, so the properties of this first homology group were nice actually, because the abelian statistics didn't depend on n, on the number of particles. There were different statistics possible in different regions of a graph, and but we are lacking physical model. So we are lacking the physical model to realize those statistics on graphs. Okay, so now we are trying to see whether there are any higher dimensional non-abelian statistics possible on graphs. So this requires computing higher homology groups, and this is what we did last year. And this is actually it's a developing thing, and it's being developed also by different people, by other people by other mathematicians, and there are more and more papers popping out that regard this topic. So there are 3 more papers about the same topic, like from this year. So okay, so that's all that I wanted to say. Thank you.
Raising.
Okay, so then you have
to wait for the microphone.
Exactly.
Now going back to this original idea of removing or not removing delta from the configuration space, are there any physical consequences which depend on whether you remove it or not?
So, yeah, so the physical consequences
that means that if somebody is using this formalism, can he tell or she tell whether one approach or the other is the correct one to describe physical phenomena?
Yeah, so when we exchange particles, it's like...
So what is the measurement that will tell which approach is correct? Professor Maciążek has a lot of wave functions for many bosons, and the question is he removing delta or not when he wants to describe experiments? No, we are not removing. Okay, good. Thank you.
Also comment, because Professor Maciążek's functions live on a different configuration space, because he never divides his configuration space by the action of the permutation group, and then he does.
Of course, all the time.
This is what he does for.
No, but so look, if you. Okay. No, but look, so if you, because these are actually conceptually 2 different approaches. You can either consider a normal configuration space, which is just a Cartesian product, and then you can impose some symmetries on the wave function, or you can consider a configuration space which has built inside it this kind of symmetry, and then you don't have to impose any symmetries on the wave function, because they are already built on the level of the configuration space. So these are 2 differences. And of course, there is no, if you don't subtract this diagonal, then of course you will get different physics.
So which is correct?
Which is correct, yes.
Which
is correct?
Of these 2 approaches,
This is the question.
No, yes, I think the correct one is...
Which
The correct one is to remove the diagonal.
The word which. Can I make a comment for those who have not understood this lecture? The concept of a fractional statistics is something which is very physical. And there are lots of physical phenomena where this question is important and can even be measured. And the simplest case is a simple conductivity of a piece of real metal. A real metal is a lattice, and that lattice is full of distortions, real physical distortion, because matter physics never creates ideal materials. So no crystal which exists in the Earth is a really ideal crystal. So if it's not ideal, it has something which the physicists call defects. And they are topological in the sense that the crystal with the defects is not described by the simple geometry, but the geometry which contains this word of a torsion, which is used in the general relativity or in differential geometry. And the symmetry group of a crystalline lattice, which is a direct, semi-direct product in this. I also know a bit of mathematics. It's a semi-direct product of a rotation group and the three translation groups in each lattice direction in three-dimensional space. It is different in the real world because these three translations are distorted in some sense. And this is a topological distortion. And the electrons, when propagated in the lattice, have a different conductivity than the electrons propagating in the ideal lattice. And that there is a contribution to the resistivity of a metal which comes from this. It was measured since ancient time where people were measuring, and nobody cared about calling it a contribution from whatever you call it. But now we understand that this is related to the topological properties of that space. And the other problem is that the physicists learn how to manufacture two-dimensional systems. Two-dimensional systems which are in a magnetic field. And then the particles in that two-dimensional world moving in this, first there was a quantum Hall effect discovered by von Kissing, which was not fractional, I mean, integer quantum Hall effects. And then they find out that there is possibility of having a fraction quantum effect. That means that the conductivity is not like in the Ohm law. Those of you who have been in the high school some years ago might remember Ohm law. Now it is forbidden to teach children, so next generations will not know it. But there was this is a linear. Now in a quantum Hall effect, the resistivity is having a plateaus. And these plateaus in von Kissing integer quantum Hall effect were numbered with the integer numbers. In the fractional quantum effects, for some reason, they can be measured by non-integer numbers, right? And now, if you have the simple electrons moving in that magnetic field, we can also measure the conductivity. And that conductivity is different. And that difference can, if you want, describe by the fractional quantum effects. There is a unitary transformation which maps the system of electrons in the external magnetic field in two dimensions into independent particles which do not obey real statistics. And the whole difference between the mathematicians who describe it in the fantastic words and the physicists is that in the physics we know that there are no electrons which do not obey the Fermi statistics or bosons who do not obey the boson statistic, but there are composite objects. Yes, sure. And these composite objects, and then the problem, what means that they occupy the same point is meaningless because the notion of the
position of the fictitious any ones is completely spurious notion, because electron sits at one point and the flux sits somewhere, and then and by canonical transformation I attach to it the number which I call the position. So that's me. So that was a slight comment for those who want to know some physics.
So we actually, thank you very much. We actually don't have time for more questions. Let's thank Tomek once again, and that's